series and figuring out what is the best test to use for that series in order to prove that it's convergent or divergent. We're also going to get to a point where we look at a series and maybe you can use 3 different tests for that same series, and you want to be able to choose one that's going to be the most efficient and the easiest one to use. So we started off talking about the nth term test. And the nth term test is just a test for divergence. You cannot prove a series is convergent using the nth term test. Main thing about the nth term test, if your limit of the term is not 0, then you know automatically it diverges without any more work. If your limit is 0, then we don't know anything and we would have to find a different test. And so far we've looked at 2 different tests. These are 2 special types of series that we have. We have the geometric series, which is when we are finding the sum of a geometric sequence, and we look for the common ratio. The geometric series is the only one that, if it converges, we can actually find its actual sum using a formula. And then we also have the p-series, which is another special type of series where we look for that p-value, which is coming from like power series, representing that constant power that we see. The test that we're going to learn today is not going to be a special type of series. It's just going to be like another one to try, and it's going to be called the integral test. So it's going to be used when you don't have a geometric series and you don't have a p-series. Before we get into the integral test, I did want you to try a few on your own. If you're looking for this page in OneNote, it's going to be the warm-up page directly after the one that says 30-p-series. But I do want you to edit one because I shared a series that's kind of a weird one. So when I shared it with you, that first series was the sine of pi over 0, or excuse me, the sine of pi n, which is kind of a weird series because it's just a bunch of zeros if you worked it out. Change it to a cosine for me and then try those 3 for me. Again, any series test that we have learned can be used, and I just want you to look at those 3 series and determine whether or not they converge or diverge. And then practice, whenever you have that final answer, just practice writing that statement of what you would use to justify your answer. And so far, the only tests you have for your options, you have the nth term test, the p-series test, and the geometric series test. So take a moment to try those 3, and then we're going to move into the integral test. And again, if you're trying to determine which test you use, like obviously nth term test is one you always want to consider first, because if your limit is basically anything other than 0, then you know automatically it diverges. But you also just want to pay attention to see, does this look like it could possibly be rewritten as a p-series test, or does it possibly look like it could be rewritten as a geometric series? And then once you figure out which test to use, write out your statement to justify it, and then draw your conclusion from there. All right, so if I'm looking at these series, this first one is just a series of the cosine of pi times n. If we want to try the nth term test, we do the limit of basically cosine. What do we know the limit of cosine is? Does not exist. Why is it, Dini? Just to review that from unit 1, way back when. It's oscillating, so it's basically going up and down forever, bounded between -1 and 1. So the limit is dne. Why is that important? That is not equal to 0. So the series diverges. I think that makes sense if you actually list out the series. So if I have this series as defined by the cosine of pi times n, starting at n is equal to 0. So you first have the cosine of 0, which is 1. Then you jump up to 1 to the cosine of pi, which is -1. Then you're at the cosine of 2 pi, which will be back at 1, -1, and that's going to continue forever. That's actually the series that has a special name, but it would be divergent because at one point it'll be 0, and then immediately after it'll be kind of like at 1, and then cycle back and forth between the two. Looking at this middle one, big clue about this middle one is we see n in the exponent. Whenever you see something that looks exponential, it's probably going to be a geometric series. In order to justify it, though, you do need to identify clearly what that r value is, the common ratio. I would rewrite this one personally, so I have like 4e to the n. Using properties of exponents, that pi raised to n minus 1 is the same thing as pi to the n times pi to the -1. I know that if I have the same base, I can add the exponents, so like pi to the n times pi to the -1 would just be pi to the n plus -1 or n minus 1. So rewriting it, I'm going to jump below what I wrote. I have 4 pi, that's kind of like the a value. Your r value ends up being e over pi to the n. So you would want to identify that and then write your statement. The absolute value of r is equal to e over pi. Well, e is about 2 point something, pi is 3 point something, so what is that r value? Less than 1. That's the important part. Since it's less than 1, series converges by nth term, not nth term test. What am I doing? Try that again. Converges by geometric series test. But what I should do is over in this first one, include by the nth term test. There we go. And then this last one, trying the nth term test, you would want to find the limit of the terms. What is the limit of the terms for that last one? -1. So again, you're thinking about what matters most. You get -1. Why is that important? That is not 0. So series diverges by the nth term test. So those are ones we have so far. There wasn't a p-series one there, but we'll hit those eventually this week. So again, all the other series for the most part that we're learning are not going to be a special type of series test. Like we're not going to just look at geometric ones. We're not going to look at just p-series. So we want to have different options for all the different series that we can encounter. The next test that we're going to cover is called the integral test. So I'm jumping to this page in the notes since where I did the p-series test. The integral test does use integrals. I think that's pretty obvious by its name. And what the integral test says is basically if we want to see if a series converges, then we can basically find whether or not an integral that is related to the series also converges. Do want to be clear, the series and the integral are not the same thing. One is adding up like discrete numbers, so like a first term plus a second term plus a third term, while the integral is like the continuous area from the starting point to infinity. So they're not the same, but they are related. And basically to use this test, we know that all the tests have some requirements. Like for a geometric series test, it has to be a geometric series. For the p-series, you of course have to go with the p-series. In order to use the integral test, the function that we're writing that is going to be related to your series has to be 3 things. And the 3 things that it has to be is it has to be continuous, it has to be positive, and it has to be decreasing. And then I'm going to emphasize the word eventually. So the only time you can use an integral test is that when you look at that formula for the terms, you're going to find its equivalent function basically. And when you look at that integral, that function that you're dealing with has to be continuous, it has to be decreasing, it has to be positive eventually. So it doesn't have to start off being positive, it just has to eventually be positive. It doesn't have to start off decreasing, it just has to eventually be decreasing. This integral that we have, clearly you can kind of see it's an improper integral. So we are going to kind of review how to find the improper integrals, which we did. Like the first kind of thing that we did back in Unit 7, so at the beginning of the semester. But that's basically what we're going to be looking at. So what do I mean by continuous, positive, and decreasing eventually? Sometimes you're just asked to determine whether or not the integral test could be used. So like if we're looking at these two graphs would represent some function f of x related to a sequence or series. This first one is kind of like the obvious one. This is like the perfect case. This function we see is continuous, it is decreasing, and it is always positive. And again, when we're talking about these series, we're never going to go back into the negatives. So like it clearly is true for all of that. The second one though, it is always continuous. Like we can see that there are no gaps in it. It is decreasing. It's not decreasing always, but it is decreasing eventually, which we can kind of see at the end of the graph. So that would work as well. Also dealing with positive. It's not always positive, but it is positive eventually. So this would also be able to use the integral test for. So even though it starts off being negative down here, it does end up eventually being positive and then stays positive as you go down towards n approaching infinity. So that's what I mean by eventually. When it comes to using this test, often you just need to say that statement. You don't have to prove it. You just have to say something like f of x is continuous, positive, decreasing. Check. Done with that, and then you can go ahead and move into the test, which is kind of nice. To summarize the test, and again, we'll kind of do this for each of the tests that we have. For the integral test, again, your function f of x has to be continuous, positive, and decreasing eventually. And this one will basically have two things that can happen. You're going to use the integral, so you're going to look at the integral. And if your integral converges, then your series is also going to converge, which I think kind of makes sense to us. Or you'll find your integral, you'll work it out, and if that integral diverges, then I think it makes sense that the series is also going to diverge. Some mistakes I see with the integral test, so we are going to have to be careful when we go to actually prove it, because we have to kind of label things correctly, and there is a lot more writing involved than you probably would like, but again, these are going to be formal proofs. One thing that I often see students make a mistake on is they want to say that the series is the same thing as the integral. So like when we are comparing the integral, the value of that integral, so like if it converges, you could get a number, and that number would represent the area of it. That number is not the same to the value of the series that you would be dealing with that's kind of equivalent to it. In fact, you can kind of figure out whether that series would be more or less if you think about how the integral test works and is allowed. So the integral test can only be used if your function is continuous, positive, and decreasing eventually. So f of x would eventually have to look something like this. That's not the series. The series is going to be finding discrete values of the graph. And we can actually, we'll imagine the series is actually the LRAM of the function. So which one will always be the bigger number? the series or the integral? The series. So whenever you find the integral, like you know that the series is always going to be something bigger than it. So really what this test is just going to tell us is like, hey, it converges. We don't know what it converges to, but it's at least going to converge to something bigger than the number represented by the integral. Yes, Liam?
You just had to talk about
Did, okay. But yeah, we won't ever find like what that series is equal to unless it's a geometric one, but who's using the integral test for a geometric series? You could, but you're wasting your time. So let's go ahead and look at an example. And again, when we do an example, I think it's just as important not only to like get to the right answer, but making sure we form our answer correctly. So I have used the integral test to determine whether that series of 1 over n squared plus 1 converges or diverges. So looking at it, how we're kind of making a decision of like what test to use. Like looking at this, I can quickly do the nth term test in my head. The limit of those terms, so as n goes to infinity, what is those terms going to? 0. So nth term test tells me nothing. So when I try something else, well, not an exponential, so I can't use the geometric test. Almost is a p series, but that plus 1 is throwing it off. So our only option right now is to try and use the integral test. Plus, it tells us to use the integral test. But that's the one that we're going to try. And so there's several things you're going to have to do when you're using the integral test. The first thing is you're going to have to state the function that you're going to use to justify your answer. So if I see this as my series, we'll have to clearly state what the f of x is that we're considering. Well, what is the f of x? You just look at that series and just change the n to an x. So the function we're looking at is 1 over x squared plus 1. And then we also need to state that that function satisfies the condition. And some students always ask, like, well, how do I know that's continuous, positive, and decreasing eventually? Several ways. Either you will know what the graph looks like. I don't know if y'all know what this graph looks like. I know I do because I've been doing math forever. But if you don't know what the graph looks like, it would probably either be provided to you and say, like, okay, here's the graph of f of x, or maybe it will be like on the calculator section, and you can just graph it real fast just to make sure that it does satisfy those conditions. Either way, you need to say that it does satisfy those conditions. So I have like f of x is equal to 1 over x squared. That's the graph that I'm looking at. And that graph is continuous, positive, and decreasing. If you want to be safe, stick eventually on after that. This graph, just if you're concerned about what it looks like, it's one of our like bell curve functions. So it does look like that. So if we're looking at from 0 to infinity, it is continuous, it's positive, and it's decreasing. And again, wouldn't have to say eventually for this one, but it wouldn't be wrong if you added it because it's kind of always positive, continuous, and decreasing on that interval. So that's the first step. And again, you would have to say that statement before you can do anything else. And then if you're using the integral test, remember you're using an integral to determine convergence or divergence. So I'm going to go ahead and write down, we are going to consider, and then write down the integral that I'm considering. And this integral, again, we look at the sigma, starts at 0, goes to infinity of 1 over x squared plus 1 dx. And then we just want to do like the work of actually finding that improper integral. So remember, when you find an improper integral, you first have to find the antiderivative. And then you are plugging in the top minus the bottom, but you're going to write them as limit expressions. So this is my integral. What is the antiderivative of that integral? What's the antiderivative of 1 over x squared plus 1? Arctangent. So not natural log, because the difference in the degrees is more than 1. But it is the arctangent of x. And then we're going to plug in the top number minus plugging in the bottom number, but we're going to infinity. So we're going to look at it as what's the limit as x goes to infinity of that antiderivative. And then what's the limit as x goes to 0 of that antiderivative. Let's do the easy part first. I'm going to do the one going to 0. What's the arctangent of 0? 0. We know that one. Have done this before, but let's kind of think about it. What would be the limit as x goes to 0 of arctangent of x? It's pi over 2. Two ways you can kind of figure that out. You either remember what the graph of arctangent looks like. So the graph of y equals arctangent is basically the tangent function on its side, bounded between two horizontal asymptotes of negative pi over 2 and pi over 2. Or you think about the unit circle. Arctangent can only exist from negative pi over 2 to positive pi over 2. So when I say the arctangent, again, this is kind of going on in my head because it's really bad notation. The arctangent of infinity, that basically means the tangent of something is equal to infinity. So that infinity is kind of like the slope of the line. So it's a very, very steep slope. And that's where the pi over 2 is kind of coming from. Or just memorize, as arctangent goes to infinity, it's pi over 2. Again, then we want to actually say what that integral is. So would this integral diverge or converge? It converges. So we would have to state that, because again, that is like what we found, and that's what's important. So I'm just going to go ahead and write a statement. The integral from 0 to infinity of f of x dx converges to, and I want to say what it converges to, top minus the bottom. So the series also converges by the integral test. And there's not an abbreviation for integral test. And that's the work that we're going to have to use to kind of justify using the integral test. Definitely a lot more kind of writing, but kind of go through again all the steps just to make sure when you're doing it on your own, you include it. So your first step is you're going to have to define the f of x you're using and say it meets requirement. So that's the first thing you're always going to start with when you have the integral test. Second thing you have, you're going to have to write down the integral that you are considering. Then you have your work. These are improper integrals, so they do require you to show some work to find them. So you have like the antiderivative, you have the limit at the top and the bottom. And then you finish it, so you're going to have the convergence statement of the integral. And then you're going to have the convergence statement with the named test of the series. And of course, that would be if it's convergent. If instead that integral diverged, then of course your series would also diverge as well. Not sure if I say this, but this is probably my least favorite test to do, because I think it is like the most writing and the most cumbersome to do. It does work, but again, we're going to be learning a lot of different tests. You do need to know all the tests. I will say personally, if I had to determine whether this one converges or diverges, I would choose a different test, probably one of the ones that we're going to learn tomorrow instead of the integral test. When would you choose to use the integral test? Honestly, if you have a problem that's really easy to integrate, then that's probably going to be the best place to use the integral test. But again, you would still want to make sure you kind of go through all those steps of things you would have to show. Questions on that?
Is the arctan not oscillating like cosine is?
Say it again, then.
Is the arctangent graph not oscillating like the cosine graph does?
No. Arctangent, this is arctangent. This is the graph I have in orange right here. That's just the graph of arctangent. That's all it looks like. Like tangent, looks something like this forever. When you're doing the arctangent, it just uses one of those to define the graph. That's why you have the domain restrictions on it. And even then, like if we had arc cosine, arc sine, those don't oscillate either because those have restrictions on their domain and range. Alex, you had a question?
Yeah, the two statements at the bottom, are they like completely separate or are they just kind of like?
You need to say both. So like why we have to have both is the idea behind it is we can't say the series converges unless we've clearly stated that the integral converges because they're going to do the same thing. So like you could probably get away by saying like since so the integral the integral converges so the series also converges and try to write it as like one sentence. It's just kind of better if you think about this as almost like a proof. We have like this is what's true, and then the next line this is what would be true because that previous statement happened to be true.
All right.
Any other questions on that? I do find that students often run into issues with this test not because of like they're determining convergence or divergence, but because they forget at this point, we haven't had to do it in a while, actually having to find antiderivatives, which actually you'll probably see. I chose problems in the bookwork to kind of force you to do some rules you probably haven't seen in a while. But that's where I'm going to go ahead and stop today's notes at. Did want to go ahead and kind of summarize, make sure we're all clear at where we're at. Each day we're learning like 1 to 2 more tests of convergence, except for the nth term test, which is a test for divergence. Please don't get behind on homework. These topics are going to build on each other. Today you can go ahead and start homework number 3. It's 1:11 now, so honestly, some of you might be able to get a good chunk of homework 3 done pretty quickly, especially if you're pretty fast at finding your antiderivatives and those improper integrals. I will say the topic we're doing tomorrow, the comparison test, hopefully by its name, you can see that you are going to be comparing it to other series, and it will help you out the most for tomorrow if you have finished homeworks 1 through 3, because you can't really compare it to other series if you're not so good at talking about the original series that we've done. And I did realize yesterday, I guess I left off number 24, I think it was 24.
Yeah.
It was one of the numbers I left off that I had assigned, and just don't worry about it. But yeah, y'all can go ahead and get started on that homework. Definitely let me know if questions. You want to go ahead and start making sure you have these series and these tests kind of memorized, because we do have like still a lot more to go. So we have 2 tests to learn on Thursday. We have the alternating series and the alternating series error bound to do next Tuesday. And then we have the ratio test to do on Wednesday. Your quiz over the convergence of series is going to end up being on Friday of next week. So yeah, y'all can go ahead and get started with homework. Definitely let me know if you have questions. And again, it's going to be most beneficial for you tomorrow if you are able to get all of homework 1 through 3 completed before we get to the comparison tests. But please make sure you're getting questions answered as they come up.